Welcome to the presentation of aliasing artifact reduction in spiral real-time MRI. Real-time MRI is a powerful tool to study the production of human speech. Time-efficient spiral sampling is usually used to achieve a high spatial and high temporal resolution. However, for the mid-sagittal slice imaging, a common artifact always presents, negatively affects the visualization of articulator movements. With an extended FOV, we can see that this artifact is the aliasing of a suspicious hotspot outside the FOV. A major cause of the hotspot is gradient nonlinearity. Here, we use the X-cat phantom to demonstrate the aliasing. With a gradually flattened gradient profile away from the magnet isocenter, a large area of the signal will be encoded to the same spatial location, causing image distortion and signal enhancement. Even though we acquire the data with a coil array that has low sensitivity below the vocal tract area, the hotspot still exists due to its high signal intensity. And for spiral trajectory, the readout low-pass filter does not fully eliminate the signal outside the desired FOV. As a result, the spiral aliasing artifact appears within the FOV as pointed by the orange arrows. To mitigate this aliasing artifact, we have proposed and evaluated two methods. For both methods, the first step is to identify the hotspot. To do so, we temporally combine the data and reconstruct the image with a 2.5 FOV. This FOV was selected to include the aliasing source for the speech datasets and may need adjustment for other applications. This image is coil combined and smoothed to use thresholding to find a mask of the aliasing source. From there, we can perform the first aliasing reduction method, the large FOV reconstruction. This method keeps a 2.5 image FOV during the reconstruction, but only reconstructs the signal within the square root of 2 circular FOV and the aliasing source mask. The second method applies the mask on the coil images and estimates its case-based signal. This signal is subtracted from the raw data to obtain aliasing-free case space for further reconstruction. To evaluate both methods, we performed a two-round evaluation by two speech experts. 54 subjects from the speech open dataset were involved in this study. In the first round evaluation, 54 videos without correction were presented to the observers with a randomized order, and these videos were graded to a 5-scale Likert score, with 1 being the least and 5 being the most severe artifacts. We then pick 5 datasets from each level and add the LF and ES reconstructions to form a 75 dataset for the second round evaluation. Here is one example result. This dataset was graded 5 and 4 before correction by 2 observers, and graded 2 for both correction methods and by both observers. A closer look at some of the frames on the right reveals that ES correction is more effective in reducing the artifact than the RF correction. Here are more results. Expert scores are displayed on the corner of each image. Generally, both methods can reduce the artifact for any artifact level. For datasets without aliasing artifacts in the first place, the methods do not degrade the image quality. As an overall result, the first round evaluation has found 79% datasets had spiral aliasing artifact. The average improvement in the Likert score was 1.25 for the RF method and was 1.35 for the ES method, with the ES method has a faster reconstruction time. As a conclusion, we have demonstrated that gradient nonlinearity causes a signal hotspot outside the FOV, and the low-pass filter in spiral sampling does not suppress it effectively, resulting in spiral aliasing artifacts. Two proposed methods, the large FOV and the estimation subtraction method, can greatly reduce the aliasing. The ES method is more effective and more time-efficient than the RF method in suppressing the artifacts. These methods may generally be applied to spiral imaging in which the desired FOV is smaller than the signal-producing region.